Hey there. Let's talk about paths inside of a graph. Okay, so first thing that I'll say is you probably should have watched my other videos already so that you understand at least the basics of graphs, or maybe you already know and you just came here for a little extra. Let's just draw a sample graph here. I'm going to do like random nodes. Let's see, what am I supposed to do? I'm supposed to like full screen that. I'm going to draw some random nodes with some random values inside of them. So I'm just going to do like a 3 here, maybe like a 3, yeah, like that. And then I'm going to duplicate this a few times. So I'm going to go, this is a valid graph. It's just not a connected graph as we talked about in my last video. So I'm just going to do this. I guess that's okay. I'm going to change all these numbers, even though your graph should be able to support duplicate values in the nodes. It's going to be really hard to explain. So I'm just going to change all this stuff. 9 here, and then like a 22. I think that's probably good. So I'm going to do this and this. Okay. So still a valid graph, but there's no chance that we could have a path anywhere in this entire graph. So that sucks. We could, by the way, do a path with an undirected graph, but I kind of feel like I want to do direction on all the edges. So let's see. Let's do direction and also weight. I'm going to like draw an arrow here, and an arrow here, an arrow there. I'm going to draw edges first in a way that that kind of makes it feel like I could find a path almost anywhere I want. So I'm just going to like draw a bunch of edges. Maybe like another edge over here. Nope, that's wrong. How about this? Maybe another edge going up here, and an edge going up here, and an edge going down there. I'm just going to draw a whole bunch of edges in the hopes that we'll have a decent graph with lots of path possibilities. Okay, I guess I've almost drawn a complete graph already. Oh, no. This is not a complete graph. I've just drawn a graph where you can kind of get everywhere. Okay, so, well, I mean, what is a path? It's just sort of like, some sort of a representation of how do you get from one start node to some destination node, like a map. So the first thing that we could do is we could say, let's make a path based on nodes. So I'm going to say node-based paths. Let's start off with, actually, let me get rid of this and put it on the next slide. We'll do this, duplicate it. That way I have the original. Let's pretend that our path is going to be just a list of nodes that we travel through. So I'm going to say a node-based, and we'll have one path. We'll say path 1. And then path 2, maybe we'll do like a second path. And well, at first we might think this is totally fine, but later on it'll get confusing in terms of which edge did we actually take. So let me show you what I mean. I'm first going to add weights to all the edges. So I'm just going to do like, a 4 and a 3 over here, and then like a 1 and a 2, then a 1, and then like a 6, and then like a 4. I'm just adding random weights or random costs to all of the edges. And then eventually, let's see, when I finish doing all of that, eventually we can probably realize that we could add more than one edge going from the same start to the same destination node, but give it a different weight so that we have a little bit more of a choice. So suppose, for the sake of argument, that we have this 6 and the 4 here. The 6 can go to the 4 at a cost of 4, but maybe the 6 can also go to the 4 with a different cost, maybe a cost of 1. I don't know why it's there. I don't know why the 4 is there also. We'll just say this is our graph. So you can have edges like this that go to the same start and destination nodes, but have different weights. So a path that is based on nodes doesn't really have enough information to tell us which edge we took. Let me show you what I mean. So suppose we want to get from node, I don't know, node 3. I'll put an S here for start. And then I guess I'll put a D for destination, or donut. I'll put a D there on node number 22. So we'll say we're going to go from node 3 to node 22. So start and destination. A path-based a node-based path, path 1, we could say maybe let's go from the 3 to the 1 to the 6 to the 4 to the 12 to the 9 to the 22. And that tells you all the nodes that you would hop on. Another path could be, let's see, that first path when we went from 3, 1, 6, 4, 12, 9, 22. When we go from the 6 to the 4, we could have a second path here that goes from 3 to 1 to 6 to 4, but takes a different edge. This is kind of what I'm trying to show you. Notice that we have two different paths. I'm going to do one in maybe red. So it's going to be 3, 1, 6, 4. So from 3 to 1, and then 6, and then we'll travel along that 4 edge. Once we get to the 4, we'll go 12, and then once we get 12, we'll go 9, and then 9 to the 22. Okay. Then the other path, path number 2, let's say that we chose the other edge. We chose the 6 to the 4 edge that only cost us 1. So it would kind of look the same for the most part, except when we finally get to that other node, we're actually going to be going this way, right? And then we're going to go up and then to the right and then down. So if you look at this carefully for a little while, maybe pause the video. These are actually two totally different paths with two totally different costs. So, you know, the cost of the orange, let me write it in orange. It's going to be 5 plus 1, so 6, and then a 7 there, and then 8, 9 there, and then I guess like a 15 there, and then a 16 there. So the cost of the orange path is going to be 16. If we switch to the red path, the only difference is the choice of edge we took between the 6 and the 4 node. So we would increase our cost by 3. So the red path would be a cost of 19. But how can you tell the difference in a path that is based on a node? It doesn't have enough information, right? So what we're going to do instead is we're going to use edge-based paths. In some places, you know, you can use node-based paths. That's totally fine. But for me, I'm going to say let's do edge-based paths. Edge-based paths. And now we just have to figure out how to add that extra information into the path. So going from the 3 to the 1, we're actually traveling along an edge, right? We're traveling along that 5 edge. So let's just stick a tuple in there. A tuple meaning just a little collection of values. For those of you in C++, if you use std pairs, that's really a tuple with 2 items. We're going to use 3 item tuples. Tuples not always limited to 3 items. It could be 2, 3, 4, even probably 1, or much more. So I'm going to say let's use a tuple that has 3 items per item, per tuple. And we'll just say that we specify the start node and then the destination node. So we start at 3, we go to 1, and then the weight of the edge that we choose to travel along. So in this case, there was only one choice for an edge, but we're putting enough information into our hop that this can be considered an edge-based path. So when we go to the 1 node, we ended on the 1 node, sorry, we've gone to the 1 node, we just ended there. So we could start on the 1 node for the next tuple, because then we're going to go to the, what are we doing first? Red? I think we're doing red first, yeah. We go from the 1 node to the 6 node. So I'm going to go comma 6. And then we choose which edge to travel along. That's just the 1 edge. And so 161 means start at the 1 node, end at the 6 node, and take the 1 weighted edge. Then do the same thing again for the next tuple. So we're at the 6 now. Where are we going to go? We're going to go to the 4, and then we choose the edge that costs 4. And then for the next tuple, we're on the 4, and we're going to go to the 12. So I'm going to say 12 is the destination. And which edge did we choose? The 2, even though there's only one choice, at least we have enough information for all edges in our entire path. So then again, we're at the 12. We're going to go to the 9. So I'm going to put a comma 9 there. And then we choose to take the edge that, what was that cost? 6? I can't read anymore. Let me actually just look real fast. 6. I guess I overwrote it. I'm just going to assume that it's a 6. I guess I could erase it real fast or move it or something. Okay, let's see. What is that? Yeah, it's a 6. Okay. So we're on the 12, we're going to go to the 9, and we choose to take the edge that costs 6. Then we're on the 9, and we choose to go to the 22 using the edge that costs 2. And then this last thing doesn't need to be done because we have the entirety of the path in our edge-based list. So I'm actually just going to copy paste this entire path and stick it into the second path, because remember, the only difference between the first path and the second path that we chose is when we were going from 6 to 4, we chose the 1 edge instead of the 4 edge. So now look at this, I can just change that 4 to a 1. And now we definitely have 2 different paths. And because we're using edges to describe our path, we can tell the difference. You know, in a computer program, we would know exactly which edge to travel along, or even just a user moving their finger along a graph or whatever. So in my opinion, edge-based paths are a little bit better. They're also better because if you practice writing down edge lists like this, then you get a lot closer to a representation of a graph in your machine called an edge list. So in an edge list, oops, I put ed light. I don't know why I did that, and now the computer's not responding. So my mistake is immortalized. Edge list representation of a graph is basically a graph is equal to a tuple where one item in the tuple is a list of vertices and another item in the tuple is a list of edges. So if you learn how to do edge-based paths, then you're already a step closer to being able to represent a graph inside of your computer program in the machine. So another thing that I want to point out is that since this graph has direction, the order of the start node and the destination node absolutely matters. For example, if we have this 3, 1 here, indicating we start at 3 and we end at 1, well, that means there must be an edge that points from 3 to 1, otherwise this is an invalid path. If for some reason, let me get rid of this here, there's too much stuff on the screen. We switched the 3 and the 1, like if I said, 1, 3, this is invalid. Because it's saying that we have to start at the 1 node and end at the 3 node, but the 1 node has no edge going to the 3 node, so this is totally invalid. Does that make sense? I hope it makes sense to you. If this was an undirected graph where every single edge did not have direction, then the order actually wouldn't even matter. You would just have to check in both directions to see if an edge existed. So let's see, we talked about different paths. Typically you would want to choose the lowest cost path, but there are algorithms that we can use in future videos to compute paths. Let's see. Something called a simple path is where every single edge in the path is distinct. So for example, I don't know, let's say we had like a really gross path here. Let me get rid of some of this. Get rid of the oranges maybe. So that this is slightly easier to read. Let's see, did we choose, I have to fix this. Let's fix the 3 and then the 1. And then we chose the 4, so this is the red path indeed. So a simple path is, nope, I accidentally erased like an extra edge or something, so I got to do one from the 4 to the 12. Okay, let me just do that real fast, from the 4 to the 12. At a cost of 2. Okay, so a simple path is something where you don't repeat edges. So I can also write down simple path here. Simple path. If this was not a simple path, then we would just basically have to repeat an edge somewhere. So if any of the edges or vertices were repeated, this would not be a simple path. So let me just, let me just update this real fast. Let's say we do, what should we do? Let's do, I don't know. When we go from 3 to 1 to 6 to 4, let's go back from 4 to 6, and then we'll take the other edge back to 4, and then we'll go up to 12. So this will be like not a simple path. If we say, gosh, I should have written this down before I drew it. 3 to 1, and then 1 to 6, and then 6 to 4, and then 4 back to 6. Okay, so I'm going to add another tuple. So starting at 4, going back to 6, and taking that 3 edge, I think is what we're looking at. And then another tuple to get back when we go from 6 to 4, and then take the 1 cost edge. And then once we're at 4, then we can go 4 to 12, at a cost of 2, and then 12 to 9 at a cost of 6, and then 9 to 22 at a cost of 2. Okay, so, I mean, I'm just saying you can make a path where you just repeat a whole bunch of edges and nodes, and you're just like going in a circle forever, like whatever you really want. It's not necessarily going to be an efficient path or something that an algorithm should produce, but you can have a path like that. Maybe your character is just going crazy in the game and they're just going all over the place. So this is not a simple path because we repeat stuff. On the previous slide, since we did not repeat anything, this is a simple path. Okay, let's see. Something else that I want to talk about is a cyclic path. A cyclic path is basically a path where you start and end on the same node. Being able to find a cyclic path in a graph is a way that you can prove that the graph is itself cyclic. Let me try to get rid of this here. Yeah, there we go. Okay, so just pretend for the sake of argument that I'm just kind of looking around and I'm trying to find some path that proves I can start at the same node and end on that node without repeating edges. So let's see. Right, so I'm gonna take the 3 and go to the 6, and then, so I want to try, if I start on the 3, then I want to try to find a way to get back to the 3 again. So I go from 3 to 6, and then I can go from 6 to 4. And then if I go from 4 to 6 over here, I'm not repeating that edge going from 6 to 4. I'm using a new edge from 4 to 6. And then I can go from 6 to 3, again, not actually repeating an edge. Now I've started and ended on the same node, which means I have found a cycle in the graph. Let me just describe this path real fast in terms of edges. So we started on 3. Oops. We started on 3, and then we went to 6, and it cost us 3. And then once we were on 6, we went to 4. So I'm going to go from 6 to 4, and we chose the edge that cost us 4. And then once we were on the 4, we just went backwards to the 6. So it's going to be 4 going to 6, and we took the edge that cost 3. Once we were on 6, we took the 6 to 3 edge. So 6 to 3, whoops, 6 to 3 edge, and that cost us 3. Yeah, did I do that right? When we go from the 3 to the 6 in the beginning, I wrote down a 3, but I should have written down a 2. Hopefully you cringed on my behalf, right? Because I think that red arrow is like on the left side, so my brain was looking at the 3, but we were really taking the arrow that points down from the 3 to the 6. So there's a 2 there. Let me just double check one more time. 6 to 4 at cost of 4, 4 to 6 at cost of 3, 6 to 3 at cost of 3. So we have started and ended on the same node, and therefore we have found a cycle in this graph, which means this graph is cyclic. What is cyclic? Just means it's a graph that has a cycle anywhere inside of it. So this is a cyclic graph. Make sense? Okay, why is this important? Well, there's kind of like a special type of graph called a DAG, which means a directed, here, let me write this down real fast on the next slide so that we don't get confused. On the next slide, I'm going to say we have a DAG is basically a directed acyclic graph. What does A mean when it's in front of something? It just means it's not that thing. So acyclic means not cyclic, and then graph. So in some algorithms, you are required to, like have a DAG before you can even use the algorithm, or if you're being tested somewhere. So let's just start by, drawing like a little bit of a graph, and we'll see if we have a graph that qualifies. So I have a little graph here. If it was empty, I don't know if you could call it a DAG or not. I think I would, because it's empty. It could be directed. So we have like a graph here. I would call this a DAG because it's a graph. We don't have any edges, but like I could assume that this would be a directed graph. But just to make this a better example, let's just say we have like 2 nodes here. And you could also probably assume that this was a DAG because you could assume that there are no edges in this graph. But if we did add an edge a second from now, then it would be directed. Not the best example, but so let's just add an edge here. Oh, actually, let's add an edge that's undirected real fast. from 2 to 6, and then maybe I'll just kind of duplicate some of these. We'll do a couple more, so I can just make this more interesting. We'll say 11. We'll say a 4 here. So ask yourself, is this a DAG, directed acyclic? Well, there are no cycles that I can see in the graph. There's no paths that you can find to kind of like end where you started. But this is it is a graph, and I don't see any cycles, but it's not directed because these edges don't have direction. So that means right away we have to upgrade every single edge to have direction. So I guess I was going to draw a bunch more edges, and now I'm just going to only draw this one edge. So this is definitely a DAG. If we just sort of do it like this, maybe another edge like this, because I don't know about you, but I cannot find any path that allows me to start and end on the same node. Let's just double check it. We'll do the 2. Can we find our way back to the 2? No, because there are no incoming edges to the 2. All right, that's good. Let me just do a check here. What about the 6? If we go out to the 6, from the 6 to the 4 to the 11, it would have been dangerous if we could get to the 2, but we can't even get to the 2, so that's fine. That means the 6 is okay. We cannot find our way back there. The 4, we can go to the 11, but we can't go any further. We're at a dead end. We can't even go to the 6. That means the 4 can't find its way back to itself, where you can't find a path that goes back. The 11 has only incoming edges, so that's automatically, a dead end. So all of the nodes qualify as we could not start and also end at that node with a single path. So that's good. That means this is a DAG, a directed acyclic graph. If you want to make this into not a DAG, just figure out how to add a path so that you end up with a cycle. So what was the first thing we did? The 2 goes to the 6, goes to the 4, goes to the 11, then it's a dead end. We could either add an edge from 11 to 2 to make a cycle, but that's a little bit too easy, right? Because if you see any pair of nodes with arrows kind of pointing back and forth between the 2 nodes, then right away that alone is a cycle. So I'm just going to maybe do an arrow or an edge pointing from 4 to 2. Then it doesn't look so much like a cycle, although it's not too hard to realize that there is a cycle in this graph. So this is not a DAG. Let me show you the cycle. We could go from 2 to 6, and then from 6 to 4, and then from 4 to 2, and therefore we would have a cycle. So this whole graph is not considered acyclic. This graph has a cycle. And if we want to do an edge-based path, we don't have weights on this graph right now, so we could describe the path as such. We could say start at 2, go to 6, and if your edge list is of a graph that doesn't even have weight at all, then you don't really need that third item in the tuple. You can just do a start node and a destination node. This does kind of preclude you from having parallel edges, 2 different edges that point from the same start node to the same end node. So say go from 2 to 6, and then from 6 to 4, and then from 4 to 2, and then we have a cycle. And that's it. Okay, I think this is all I really wanted to talk about for this particular video. In future videos, we're going to do algorithms, and then there are some others up already that have graph properties and connectedness and definitions and things like that. So leave a comment asking about some algorithm or some property of a graph that you might be interested in. Otherwise, thank you so much for watching this video. I hope you learned a little bit of stuff, and I hope you had a little bit of fun. I'll see you in the next video. Yeah, I'm gonna go eat some cookies. No, I shouldn't do that, but I'm still going to. Hey everybody, thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community, so we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. Sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe, and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video. and it'll take you to my main website where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? You know, just send me a comment, whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness, which is coming for us all.